Hi, I'm John Michelli. On the Minstrel Banjo Forum, we often talk about things that contribute to the sound of the banjo. We talk about strings, we talk about the heads, we talk about the bridges, we talk about the construction of the instrument. So I thought today I'd take a quick look at the sound of the banjo. To do this, I'm going to compare the sound of three different instruments. First of all, there's my gourd banjo. And I'm going to be comparing the same note on all three instruments. Then there's my minstrel banjo. That's 8-2-20 for those of you that are trying to figure that out. And finally, on a modern era banjo, now to analyze these various sounds, I am going to use a frequency analyzer, data physics quattro analyzer, which will allow me to do all kinds, and all the graphs that you'll see generated basically come from that. And to transduce and to measure the aspects of the banjo sound characteristics, we're going to use two transducers. One is this, which is a measurement grade microphone, and this has a very flat frequency response. And then in addition, I am going to use this, which is an instrumented modal hammer, and this is really useful to input a known force at a given spot, and then to measure the response of a structure to that force. The graph you're looking at is a waterfall graph of the minstrel banjo being plucked. The horizontal axis is frequency in hertz. The vertical axis is sound pressure level in decibels, and the axis coming towards you is time in seconds. Looking at the graph, we can see that most of the energy is below 10 kilohertz, and a lot of what's of interest is below 5 kilohertz. So we can zoom in and look at the data to a bandwidth of 5 kilohertz with a lot more resolution. If we were to rotate the graph and then look down at it from the top, we'd end up with a graph called a spectrogram, where the horizontal axis is time in seconds and the vertical axis is frequency in hertz. You can see that there's an even spacing between many of the tones in the image, and this clearly shows the harmonics in the note that was being plucked. If we zoom in to a 2 kilohertz bandwidth, we can see the first 7 harmonics. And after further analysis, I've determined that these 7 harmonics really are very important in characterizing the sound of the banjo. So we have here the first harmonic, which is at 220 hertz. The second at 440 hertz. 660 hertz. 880 hertz. 1100 hertz. 1320 hertz. 1540 hertz. If you put them all together, it would sound like this. If you apply an exponential weighting, it might sound like this. And if we compare that with the actual banjo frequencies in the same range, it would sound like this. So you can see between the actual banjo and our synthesized banjo, there are some differences. And so the question is, where do those differences come from? And what we can do is we can step through and look at the various frequency content of the measurement as we actually pluck the string. So I'm going to step forward in time here, and that's the actual point at which the string is being fully plucked. And what you can see in the lower graph is the actual instantaneous spectrum at that point in time. And what you can see the 7 harmonics isolated by or indicated by the asterisks. But then you also see that there are other very significant and prominent frequencies in here which have nothing to do with the harmonics. So the question is, of course, where those come from. And what's of interest is that as we step forward in time from the point at which the instrument is plucked, we can see that after a half a second or so, what is dominant are the harmonics, but there are still a few frequencies that are coming from somewhere else in the instrument. So we really would like to understand what those frequencies are. Let's face it, most banjo players tend to play more than one note every half a second. So, so we are constantly hearing these other tones. And the question is, what are those tones? A factor of structural analysis is that when you impart an impulse into a structure, you excite all of the frequencies of that structure. And so what we're looking at here is the resonance and the structural response of the banjo to having an impulse put in, that impulse being the plucking of the string. So what we'd like to be able to do then is to characterize the impulse of the banjo that we're playing, the impulse response of that banjo that we're playing, and to look at the frequency response of the banjo based on energy being put in at the bridge. In order to capture the resonant frequencies of the structure of a banjo, at least in terms of the resonant frequencies that you might hear when you're playing it, the best thing you can do that I have found is to lightly damp the strings with your fingers so they don't ring, and then to tap on the corner of your bridge with a hard object. I'm using the instrumented hammer here, which is what I was using to take some of the measurements you're about to see. But in any event, if you tap and tap lightly, what you'll hear is the drum-like quality of the particular banjo. The reason you do that with the strings on is because the string tension actually adds to the structural dynamics of the instrument. So it's best to just take the instrument as you'd be playing it and tap. Tapping on the bridge with the instrumented hammer and measuring the response with a microphone, we can create the frequency response function of the instrument. For each frequency, we can determine the sound pressure level out based on the amount of force being put in at the bridge. Energy input at a peak or resonance will be mechanically amplified and will ring longer. Energy at one of the valleys or anti-resonances will not be transmitted. With this consideration, we can begin to understand how each note on the instrument is unique based on where the harmonics lie. Some notes and some harmonics will be amplified and some will be deadened. As you can see by this graph, each instrument is unique to itself. What even complicates things more is the fact that the nature of the banjo can change even as a matter of a couple of hours based on temperature and humidity, as, for instance, the head becomes taut or less taut, and as the strings also might change characteristics, such as the gut strings that I have on the minstrel banjo and the gourd banjo. So all of these factors will actually change the sound of the banjo. Third octave analysis is often used when measuring acoustic signals because of its approximate correlation with human hearing. Here are third octave waterfalls and spectrograms of the three instruments. I find that there are three frequency ranges common to all of the instruments. The first is the low frequency range, which characterizes the first harmonic and lower. Then there's the middle frequency range, which characterizes the second through the seventh harmonics. And then there's the high frequency range, which is the eighth harmonic and higher. Well, that concludes today's presentation. You might say that we haven't focused on what sounds good in the instrument, but rather what sounds. What sounds good entails some of the structural properties that we've discussed, bridge material, bridge string types, and all those various aspects coming into combination, and require a lot more detailed analysis. I hope you've enjoyed what I've presented, and good playing.